In this lecture, we're going to start exploring Chapter 2 of the book, which delves into the various coordinate frames and angles that we're going to be discussing throughout the rest of the course. In this video, we're going to review transforms and discuss notation of the book. And then in following lectures, we're going to use these same slides to delve into the MAV coordinate frames, discuss the wind triangle, and at the very end, we'll talk about vector differentiation, which is really a segue into the next subject in Chapter 3, where we talk about the time derivatives of our positions and rotations. So let's delve in. So we're going to first, like I said in this video, review the transforms and discuss the notation of the book. Like we've mentioned previously, the various reference frames are used a lot in the guidance and control of the aircraft. The various reference frames make different things easy to express, and so it's really nice to be able to quickly transform between one frame and another. For example, like GPS, I might be getting readings in inertial frame. It'd be nice to know how that's affecting my body frame. For accelerometers, vice versa, I might be getting sensor measurements in my body frame, and we might want to see how that's affecting things in the inertial frame. So let's jump into rotations of a reference frame. So in this case, this is exactly what we had talked about previously, where we have reference frame 0, which is denoted by I superscript naught and J superscript naught. And then we have also our reference frame, oops, that doesn't highlight, 1, which is, again, I superscript 1 and J superscript 1. Now, the book has fantastic notation all over the place. I actually love how the book presents things. There is one thing that I dislike, and that's just here in terms of representing these unit vectors. In a previous lecture, we talked about how we would represent this as a subscript naught, and this will allow us to write in as the superscript being the frame in which we're talking about. So this, in this case, would be 1, 0, 0, J, and then if we're just using the notation of the book, we'll write it like that, right? So we'd have J naught, and if we have, well, that's not equivalent, but J naught, if we were to write it in terms of frame 0, would just be equal to 0, 1, 0, and would have K naught, if we were to write it in terms of frame 0, this would be 0, 0, 1. But it's important to note that as written here, there is not necessarily a rotation frame identified, or a frame of reference identified. Okay, but the idea here that we look at in this slide is that we're rotating our frame of reference. But we have this point P right here that's fixed. So we can either write it in terms of our reference frame 0, which would be just our x component of the reference frame 0, our y component, and our z component. Or we could write it in terms of our reference frame 1. In this case, note that we've used the superscript 1 to denote that we've changed our frame of reference. So we can see that we have two different ways that we could write this point, and realistically we could come up with, and we are going to come up with, many more frames of reference, and we could represent that same point P in each one of those frames. So in this case, what we're saying here in this line is that these better be equivalent, right? So if we have the first representation of P, we've just said that that's equal to P. Well, that means that these two are equivalent, and so we put this guy on the left half of the equation and this one on the right half. So these two had better be equivalent. Now, we're going to write various representations of this p vector. If we represent this, I called it a vector, if we represent this point P in frame 1, that's how we define point P in frame 1. If we were to come back up here and define point P in frame 0, we would have written it as Px, and we use 0, Py 0, and Pz 0. Excellent. So, like we mentioned last time, or in a previous lecture, we can talk about a rotation matrix to get us from the 0 representation, right? So this is over here, this is just P0, all the way over to the coordinate frame 1's representation. And we talk about that in terms of a rotation matrix. So this rotation matrix, R, maps from frame 0 to frame 1. So if we write that out again, we're saying that R, R0, 1, this maps a point from frame 0 to frame 1. Okay. And if we were to do it just about the k-axis, this is what we called last time as RZ of theta. So we have our elementary rotation matrix. Excellent. The book does a great job in terms of relating the unit vectors that define each one of these coordinate frames. So let's delve into that just a little bit. But what we're looking at here is that we note here, this last time we noted as we have I naught, so the I vector in frame 0, right? And if we do the multiplication, that's going to give it to us written in frame 1. This column will give us J naught in frame 1, and this column will give us K naught in frame 1. So let's dive into that just a little bit more, as well as this representation of our coordinate system. So if we take this equation right here, so we're going to start playing with that equation right there and show how first we get these individual elements in frame 1, and second, we're going to then look at how this matrix could relate to what we wrote up in a previous lecture. Okay, so what we can do here is if we just left multiply each one of our this whole equation by I1. So we're going to left multiply this side by I1, and now we're going to just stay in the notation of the book now for this part. And we'll multiply this side. So we're just multiplying both sides by I1. And we'll use the dot product to multiply. So this is going to result in Px1 of I1 dot I1 plus Py1, and we'll have I1 dot J1 plus Pz1 of I1 1 dot K1. So let's take a look at that real quick. This guy right here, we're just going to have a 1, 0, 0 dotted with a 1, 0, 0. That results in a 1. So it's just the value 1. If we look at this guy, so it's going to be a 1, 0, 0 dotted with a 0, 1, 0, right, which is going to be equal to 0. And this guy right here is going to be similarly 1, 0, 0 dotted with a 0, 0, 1, which similarly will give us a value of 0. So In other words, this left-hand side just is equal to px1. Okay, and then the right-hand side is just px, we wrote it as px naught, and we say that we have I1 dotted with I naught plus py0 I1 dotted with j naught plus pz0 of I1, I1 dotted with k0. Excellent. So we end up getting this relationship, which, if we come back to this equation right here, right, we're just doing this matrix multiplication of the right-hand side multiplied by that first row to give us px. Okay, so that, and we can do a similar thing for py. Instead of multiplying everything by I1, in this case we multiply everything by j1, and similarly for pz. So we can see now, using this simple relationship where we've written up our point in terms of in two different fashions, and we've set them equal to each other. We can quickly see that this relationship holds quite simply. Okay. The next thing we want to look at, if you recall, we previously wrote that we would have written that R01 is equal to, we said I naught 1, j naught 1, and k naught 1. Or we could write the rotation matrix to get from frame 0 to frame 1 in terms of the vectors that make up frame 0, I0, J0, and K0, in frame 1 coordinates. Okay, so let's take a look at that really quick. And we also, I made this claim that this first column, now it's starting to get a little busy, this first column right here is what I wrote up as previously as I0 written in frame 1. So let's write that down. We have that I01 would just be equal to I1 dot I0. Then we have J1 dot I0. And we have K1 dot I0. So let's look at if we have I0 and we have I1. Okay, what is I1 dot I0? Well, all this is the magnitude of the vector I1, or I naught, really you could do either one, projected onto I1, right? So that's, we get that from our dot product. So in other words, if we were to come here, that's that value. Okay, so that would be I1 dot I naught. Excellent. So we can similarly think of J1 dot I naught. That's going to equivalently be the magnitude of vector I naught projected onto J1. Right? And similarly for K1 dot I naught. That's going to be projected. Everything's the same. We're doing I naught onto K1. And so in reality, what we're doing is we're taking I naught and we're finding this is going to be the X component in frame 1. This is going to be the Y component in frame 1. And this is going to be the Z component in frame 1. So we can see that we're just taking that vector I naught and we're projecting it onto each one of the other elementary vectors for frame 1. So that's how we can relate what we talked about previously, where we have just the rotation from frame 0 to 1 is just the vectors of frame 0, the elementary vectors of frame 0 expressed in frame 1 coordinates. So pretty cool. And I love this relationship that the book so cleanly defined. One last thing that I want to motivate is this value of cosine theta there. So we have our cosine of theta represented as, if we look at that, that is our I1. So let's look at this cosine of theta term. The cosine of theta. So again, this is if we're rotating about the z-axis, where do we get this cosine of theta and how do we relate it to this dot product representation? So this cosine of theta, if we take a look at that, that was just our term here. So maybe I'll highlight that instead of having so many circles all over. So we have our cosine of theta is just equal to our, we're claiming that it's equal to I1 dot I naught. Okay, so let's get some intuition where that comes from. Any two vectors, in this case they're I0 and I1, we can define the angle between those two vectors. We'll say that's theta. This angle theta can be described in terms of the dot product. So if we have any two vectors, if we say A dot B, this is actually going to be equal to the magnitude of A times the magnitude of B times the cosine of the angle between A and B. So where we have I naught and I1. So this allows for a generalized definition of an angle in any dimension. So we can define the angle between vectors in any dimensions. So if we directly take the A is our I1, and that B, is our I naught, that's going to be equal to the magnitude of I1 times the magnitude of I naught, I should keep its dot, times the cosine, and we already defined that the angle between them is theta, so we'll do cosine of theta. Well, this is really nice because this guy is equal to 1. The magnitude of each one of these elementary vectors is just equal to 1. So we just have the cosine of theta is what's left over. So that's where we end up getting this cosine term. And you could use similar properties to start talking about sine theta, cosine, and the other, well, the cosine theta term comes in terms of relating the j-axes. Okay. Excellent. So we have this, we now have kind of taken a look at this nice relationship that we have between 2 points, or it's the same point written with two different representations, coordinate frame 0 and coordinate frame 1. Okay. Now we have, oops, looking at the wrong thing. Okay. Now we have just a summary page of our rotation of a reference frame. So again, all we're doing is rotating the axes of the reference frame from one position to another. If we rotate it about the j-axis, remember we called this previously, we called this ry. If we do a right-hand rotation about the I-axis, previously we called this rx. And then we could also rotate about the z-axis. And this guy is equal to rz, right? So our traditional two-dimensional rotation. Okay, so we have our elementary rotation matrices. And then some properties that we discussed last time in a previous lecture is that we have the inverse. If we're going from frame A to B, we take the inverse of that. That's just equal to its transpose, which is equal to the rotation from frame B to A. So property 1 is really nice. We have a nice, our inverse property. Now we can talk about chaining. So if we want to chain rotations together, we can say that the rotation from frame A to frame C is just equal to the rotation from A to B multiplied by the rotation from B to C. So we can chain our rotations together. And this property here is our property that we are in SON, where n could be either 2 or 3. So that the determinant of our rotation matrix is going to be equal to 1. So we're in the special orthogonal group. Okay, now let's talk about rotation of a vector. Now, and again, this is, we were talking about, so when we talk about passive rotation, this is of a point. So we're keeping the point in place. The point stays. The point stays. Now, for an active rotation, we're just going to rotate the vector around. So, or we could consider it as rotating the point around. So in this case, now we have P, and we want to move it by an angle theta. So we have our vector P that we've written, and we want to shift it down. So the goal is to shift P down to Q. So we want to shift that point down. And so I keep saying point, but shift that vector down. And our coordinate frame stays the same. So we're still going to express everything in terms of frame 0 coordinates, but we're just moving things within that coordinate frame. So if we took a look at what P is defined as, we could say that P is equal to the cosine of theta plus phi, assuming that theta is positive, right? Because now, so we're saying that that angle is theta plus phi. Okay, so that's how we define point P. So if we looked at this component of it, we would be the cosine of theta plus phi. And this component would be the sine of, let's say, the P times, so P, where P is our magnitude in this case, the scalar P, plus phi. So we can define P as such, so we haven't done anything, and we're assuming it has 0 z component currently. Well, we can go from here to here just using properties of trig. So we can just break up our cosine of theta and phi into these two different these two different summation components, the cosine of theta plus phi and then the sine of theta plus phi. So we're just using trig identities. And now here, we're just going to factor out. And what we're doing is we're factoring out Q, or the result, i.e. the result of our movement. So we have our result over here. All we've done is just factored it out. So on the top row, we can factor it out so that when we get P times cosine of phi multiplied by cosine of theta, right? Then we'd have the second row would be multiplied by a negative sine theta, which will give us the minus sine theta sine phi. So we have, we've just factored things out. And now we've defined Q, where Q is really where we want it to end up, right? So Q is just a rotation off by phi. So again, we're just rotating this vector P backwards by theta. Okay. Now, we can say that Q is just the P cosine theta, P sine theta. I said theta, I meant phi. Sine phi and 0. Okay, the thing that's really interesting to note is that this is the same rotation matrix that we got earlier. So if we looked at when we were rotating here, we said that for this just rotation about the z-axis, it's almost the same rotation matrix. Sorry, I slipped up. Except for that our minus for the sine term has been shifted over to that term. So if we come back down here, we now have the minus in the upper right location instead of the lower left. So this is equal to our R 0 to 1 transpose. So we've rotated it back by theta, and that's just our rotation matrix from 0 to 1 that we defined earlier. It's just the transpose of that. So when we're then rotating these vectors, if we want to rotate our P by that vector theta, then we're just going to be, it's as if we were going forward in time, or sorry, I misspoke because this is Q. So we multiply Q times that R 0 to 1 to get to P. And now if we were to get Q out as a result of P, what we would do is we would take the transpose, right? So we can move, because this is equal to R 0, 1 inverse, we can multiply both sides by R 0, 1, and we can multiply this side by R 0, 1. And we'll end up getting that P times R from frame 0 to frame 1 is then equal to Q. So we cancel those things out. Okay, because this guy, if we multiply them together, it's just going to be the identity matrix. So now what we've done is if we wanted to rotate P to Q, right, all we've done is multiplied by that rotation matrix. Now this is really interesting because this rotation matrix is the same one we used to go from frame 0 to frame 1, but now we're going in the opposite direction. So that's why over here we say that R 0, 1 can be interpreted as a left-handed rotation of the vector by angle theta, because we're taking this vector P and we're doing a left-handed positive left-hand rotation instead of a right-hand rotation, where again, if we define our vector, we grab by our right hand, we're going to rotate one direction, right? Going by our left hand, we rotate in positive direction, it's going to go the other way. So this is a really interesting thing. So for rotating vectors, then we'd have the same relationship. So if we wanted to rotate P backwards by theta, or a left-handed rotation of theta, then we'd use that same rotation matrix. Okay, but the big thing to notice here is that theta right here is defined as left hand So it's left hand rotation. And then we can use the same rotation matrix as we did before. Okay, so that's where the book talks about then this idea of passive versus active rotation. So again, we've chatted about that a couple different times. So R 0 to 1 defined in the passive format, right, transforms a point from one representation to another. If we consider it as a left-handed format, then it'll allow us to rotate the vector from one position to another position. Okay.